This video provides a demonstration of a graphical user interface application implemented with Linux running on the Microsemi SmartFusion microcontroller. This demo runs on the Microsemi A2F500 dev board with a TFT LCD module connected to the main board over the expansion interface. The demo implements a GUI application for an emulated home control system appliance. I'm going to show more of the GUI later in this presentation, but first let's take a closer look at the hardware setup required by this demo. As mentioned, the demo runs on the Microsemi A2F500 dev board. There is an add-on LCD board connected to the main board over the expansion interface to the SmartFusion. The LCD module has a 240 by 320 resolution supporting a digital RGB interface with 16 or more colors per pixel. The FPGA fabric of the SmartFusion is used to implement a soft IP LCD TFT controller compatible with the interface of the LCD module. The IP includes a dedicated DMA block responsible for constantly fetching pixels from the video frame buffer that resides in the external SRAM memory and placing them into a FIFO buffer residing in the FPGA fabric SRAM. Another block of the LCD controller IP retrieves the pixels from that FIFO, converts them to the format required by the digital TFT LCD interface, and feeds pixels to the LCD module at a 5 MHz rate. In other words, the LCD controller IP implements a graphical interface coprocessor engine that runs in parallel with the Cortex-M3 processor core. From the software standpoint, when a pixel is written to the video frame buffer, it is immediately displayed without the need for any further involvement from the main CPU. The LCD controller IP is configured to support 240 by 320 resolution using 16-bit pixels in RGB 565 format. For the input device, this demo uses an emulated mouse device using the 5 push buttons available on the Microsemi board. The left, right, up, and down buttons are used to emulate mouse movements, and the center button is for mouse event clicks. This type of mouse is not very convenient since it takes a lot of button pushing to move the cursor to a desired location. You will see in the demo that the mouse cursor moves around slowly and somewhat awkwardly. However, this is the only input device that is readily available on a Microsemi board, so we're going to go ahead and use this for the demo. When developing this demo, we also added support for serial mouse using a UART interface implemented using a soft IP UART block instantiated in the SmartFusion fabric. This mouse worked as a normal mouse would, but this requires a lot of setup and wires, so we decided not to show it in this video. The input device is probably not so critical for demonstration purposes, since real-life human interaction interface in all probability would be using a touchscreen or some service input buttons. Let's see how to boot the demo onto the board. I have the board programmed with the Linux configuration that implements the GUI application. Here's a real-time view of the bootstrap sequence, as shown in the board serial console. As you see, Linux takes a few seconds to boot up and to bring the system to the shell command interface with networking enabled and fully configured. Let's go ahead and start the Telnet daemon. This will allow us to connect to the SmartFusion remotely, even when the Linux console is taken as a terminal for the GUI application. Next, let's start the GUI application. This application is based on a Qt embedded library, which implements very sophisticated graphical widgets and provides a lot of capabilities overall. However, it also consumes a lot of memory and takes a reasonable amount of time to start up. These startup times will be improved by configuring out unnecessary features from the Qt library. We haven't done that yet. An alternate approach would be to use different graphics libraries supported by Linux, such as NanoX. The trade-off when choosing a library is between size of the resultant binary and startup time versus the level of sophistication you want to get in your GUI design. The good news is that Linux supports several graphical frameworks on top of the video frame buffer layer, so it should be possible to find a solution that is an acceptable compromise for any specific application. So now the GUI is up and running on the board. Let's take a closer look at what it is able to do. As mentioned before, the application makes an attempt to implement a human interface for the home control appliance. The emphasis obviously is on demonstrating graphical capabilities of Linux and Qt embedded rather than on implementing a sensible home control interface. The vertical pane of buttons on the left side lets the user choose the location he or she wants to control. The buttons at the top are for various operations the user can run on selected location. The larger area is for widgets specific to certain operations. The mouse movements are somewhat slow and jerky, but please remember that I have to push the buttons on the board to emulate the mouse in this demo. So the first widget is a list of icons. What it lets you do is select a particular icon in a list and do some operation on it. If icons do not fit in the area allocated to the widget, you can scroll to an icon you are looking for. Operation is a combination of two widgets that lets you view and edit the date and time. It is a text editor window. In my demo, I don't have keyboard implemented, so I can't really do editing, but I can view the text. Of course, this widget allows you to scroll to a certain line and position to the text you're editing. The last operation is a combination of independent dial and slider widgets. These are good for reflecting status of some sensor or changing the setting of a control. Finally, there is a push button widget that I can use to change the background in my interface. This illustrates how Qt Embedded supports images of various formats, transparent colors, etc. Finally, let's take a look at the system and make sure the GUI application leaves sufficient CPU cycles for other processes and tasks that may need to run in parallel with the GUI. Here I will log in remotely through the Telnet connection. As you can see through the PS command, plenty of cycles remain for other applications.